I would like first to introduce my co-workers. It's Professor Berto and one of his PhD students, his master students who perform a research stage in our university in Romania for his master dissertation. So most of the results were obtained by his student. We had a lot of data for mechanical properties of foam materials, and we were thinking how to apply some engineering criteria like strain energy density criteria in order to evaluate the load and the fracture load on this type of materials. So today I will start with a short introduction, then I will present our experiment. I think it's better without. You can hear me? Without microphone? Yeah, it's better without, yes? Okay, so then I will present the experimental program. We were looking on notch effect and mixed mode fracture toughness for this style of materials. Then we want to apply the strain energy approach, and finally I will draw some conclusions. Very briefly. So these polyurethane foam materials have a lot of applications today, starting from isolators in building industry, in civil engineering, in automotive engineering. A lot of parts are made by polyurethane materials, in small ships, and in packing. This is because of their main characteristics, which are lightweight, high porosity, good thermal isolation, great capacity to absorb impact energy. So we investigate many types of densities for these cellular materials. Today I will present, the most of the results that I present today are for the different densities: 100 kilogram per cubic meter, 150, 300 and 651, which are manufactured by a German company, Necummer, and they have the commercial destination Ecuron. So we can see that at low density, these materials looks like a closed cell cellular structure. While increasing the density, they go to a porous solid structure. So the cells are lower, and we have the material contained in the cell walls is higher. So we did some statistical analysis of these structures, and we come with the cell diameter, cell wall thickness, and the density of these materials. Our experimental program consists in first identification of the type of the foam, then we perform some compression tests. We look on the influence of the density, loading speed, formation direction, size effect, and the temperature influence. Then we did some tensile tests and some fracture toughness tests, where we look again on the density, on the loading speed, formation direction, notch effect, size effect. So we have, as a result of this experimental program, we have a lot of material data in compression from tensile test, and also the fracture toughness K1C and K2C. So for investigation the notch effect, we choose 3 notch geometries: a rounded V notch, lateral U notch, and circular hole with different diameters. We use our Zwick-Roll 5 kilonewton testing machine with a 2 millimeter per minute load speed at room temperature. We have here first, these are the results from the tensile without notch. So the materials are not brittle, but when we test the notch specimens, we can see that we have a brittle failure of these materials, a linear elastic behavior of these materials. These are some results of the average load on the notched specimens. We try to replicate or to obtain using the average strain energy density. So the fracture toughness test, we choose more types of specimens. I show you here the results obtained on asymmetric semicircular bend specimens. So we use the same 2 millimeter per minute load speed and our Zwick-Roll 5 kilonewton static testing machine. So we adopt this specimen because it's very simple. So you can produce mixed mode from pure mode 1 to pure mode 2 only by changing the position of one support. So when it's symmetrical, we have pure mode 1, and moving one of the supports to close to the crack, you can get different types of mixed modes and even mode 2. What we did first, we calibrate this, so we use the Frank 2DL code, and we calibrate this specimen. So we have here the non-dimensional stress intensity factor results. This is mode 1 and mode 2. We can see here that for around 2.6, the distance from the notch, we have a pure mode 2. These are some typical low displacement curves. We see that the same when we have only pure mode 1 and we have the crack. So we have a brittle behavior, so we have a quasi-brittle behavior. But after reaching the maximum load, we have a drop of the load. So these are the results for different positions of the support aspect. So we also represent our data in these fracture curves and compare with some theoretical, I didn't put here in this presentation, some theoretical approaches for fracture. So it's MTS, strain energy density, maximum energy release rate, and equivalent stress intensity factor criteria of Professor Ricard here. And what we see that the best representation of our data comes from this equivalent stress intensity factor criteria, because this is the only one which takes into account K1C and K2C, which means that in a way tune our results to have good results here for the K2C. So the large scatter were obtained for the density of 300 kilogram per cubic meter, which in the macroscopic analysis show not a normal distribution. So these are some comparison. We did other tests, 3-point band, 4-point band, and single edge crack specimen. So this is the specimen proposed also by Professor Ricard. And for mode 2, we have the compact shear specimen, and again this specimen. So the results are more or less the same. What I would like to say a little bit about numbers here. So the K1C and K2C for the low density foam are below 0.1 megapascal square meter and reach 1, or it's higher than 1 for the 651 necron, which is a porous solid already. So having these results, we try to apply the strain energy density criteria. So we have our notched specimens and our cracked specimens. So basically, we were looking to find this average set in a control volume, and we use the formulas from the literature for determining the control volume for the cracked specimens and the notch geometry. Usually this volume control is calculated with ultimate tensile stress, but in this case we have a non-brittle behavior on tensile, and using this, so we get the parameters, the volume control and the strain energy density, and comparing with our experimental data for the notched geometry, so the scatter is from plus 10% to minus 22%, which is, let's say, in the dispersion of the engineering applications. So the higher scatter was also observed for the foam with 300 kilogram per cubic meter density, and we use this for the cracked geometry. So we represent here the normalized strain energy density at power 0.5 for different foam densities and against the mixed mode parameter. So here the scatter is higher. We have quite good results for mode 1 and predominantly mode 1, but the scatter is higher here. What we try to apply an approach of Professor Severin and proposed again after this by Professor Lazarin and Professor Berto. So we determine the tensile strength for notched specimens. So we use some specimens with semicircular notches of 5 millimeter radius, and we replace in our data the ultimate tensile strength obtained in tensile with this value of the stress obtained in notched specimen, and we reprocess the data, and we can see here a much better fitting of the experimental results. What we did for the mixed mode, it was we consider the same volume control for all mixities. To conclude, we use the asymmetric semicircular band specimen to determine the fracture toughness of these polyurethane rigid foams. So, as is expected, the density of the foam is the most important parameter influencing the fracture toughness. This strain energy density criteria could be applied for notched cellular materials to predict the fracture load, and it's better to use this strength obtained on notched specimens than the ultimate tensile strength of this. So, and our hypothesis looks that works, in which for mixed mode we maintain the control volume constant and equal with the control volume from the mode 1. So most of the experimental part was done in a contract financed by Romanian government, and Mr. Picotin was supported by Erasmus Plus program to carry on this research stage in Timișoara. Thank you very much for your attention.